Let's talk about aliens. No, sorry, not like this, but how do scientists think about life elsewhere in the universe or extraterrestrial life, aka non-Earth life? But where to begin? Well, scientists love equations. Okay, maybe that's not actually true, but I love equations, and the primary equation associated with extraterrestrial life is the Drake equation. This equation is named for its formulator, Frank Drake. So Frank Drake is an American astronomer who studied astronomy at Cornell and Harvard. You may have heard of his doctoral advisor. It was one Cecilia Payne. Pretty cool. Drake created his famous equation back in 1961 at a SETI meeting, and we'll go into SETI in another video. Now, the Drake equation is not an equation in the same sense as, say, Newton's law of gravity or the area of a circle or something that you're going to calculate and get an exact answer for. It's more of a way of framing of how do we discuss the probability of extraterrestrial life. This is what the Drake equation looks like. The basic idea is to think of all the things that are necessary to have an intelligent, detectable civilization in our galaxy and how likely they are, and multiply it all together. So as far as equations are concerned, the math is actually pretty simple. So let's briefly go over what each one of these components are. N is what we're trying to estimate. This is just the number of civilizations in our galaxy with detectable emissions. R star is the stellar formation rate. Life presumably needs a star, like we have our sun, and so this just tells us how many of those stars are coming into being in the galaxy every year. Now, a complication here is whether any star can be a suitable host star or whether you need a certain stellar type. FP is the fraction of stars that host planetary systems. Life presumably, again, needs a planet like we have the Earth. Or maybe not a planet, but maybe a terrestrial type moon. But again, that moon would then need to have a planet, so that would fall under this category of planetary systems. And E is the number of planets per planetary system that are suitable for life or are habitable planets. So for example, a planetary system that only has Jupiter-like planets isn't really going to count. So suitable planets are generally considered to be rocky terrestrial type planets, or again, maybe moons. Now, FP and NE are often combined into a single term called Eta Earth, and this is just the number of habitable planets per star. FL are the fraction of habitable planets that actually go on to develop life. Just because a planet has the properties that we associate with being habitable doesn't mean that life necessarily developed there. Look at Mars. Long ago, it may have been what we consider habitable, but that doesn't mean that it has life. Fi is the fraction of those life-bearing planets that actually have intelligent life emerge. So if you copy-pasted prehistoric Earth when it just had single-celled organisms, what fraction of those copy-pasted Earths would actually go on to develop humans or dolphins with opposable thumbs or whatever, some intelligent species? And FC is the fraction of those intelligent species that would actually develop civilizations that would create detectable emissions. If the intelligent species here on Earth was some sort of uber dolphin, would they actually be using electromagnetic emissions? Would they be building radio antennae? Would they be building telescopes? And lastly, L is the lifetime or the average length of time that these civilizations are actually creating these emissions. Earth 100 years ago? No. Earth now? Definitely. Earth in 100 years? So we have a rate that's just a number for time, and we're multiplying by a time, and then in the middle we have all of these factors that are just fractions or another number. So basically what we end up with is a number, which is what we wanted. Of course, the obvious question is now, what do you get if you calculate this? What is n? Well, we don't actually know. Again, the Drake equation is more of a framework for how we think about detecting intelligent civilizations than it is something that we're going to calculate and get some sort of exact answer. So back in 1961, when Drake came up with this equation, him and his colleagues did have some rough guesses for each of these components. Now keep in mind, 1961 was still over 30 years away from the first detection of exoplanets. They basically estimated 1 or close to 1 for all of these various fractions, and then for the lifetime they estimated about 1,000 to many millions of years. This meant that the original guess for n was somewhere between 20 and 50 million. And although we have learned a lot about all of these factors since then, we still haven't actually narrowed that estimate very much. In fact, if anything, we might have broadened it because some people argue nowadays that n might be as low as a trillionth. Now, of course, n is a number and a trillionth isn't really a civilization, but that would just be saying basically n is 0 and we are a total fluke. Now, Drake himself actually currently estimates n as approximately 10,000. And the reason for this wide range is because estimating each of these components of the Drake equation is incredibly challenging because it involves many different scientific fields and we have so little data. We know of exactly one intelligent emitting civilization, our own, and we don't even know how long that is going to last. But the Drake equation is definitely serving its purpose of helping scientists discuss these challenges and what we do and don't know about extraterrestrial life. A search of Google Scholar reveals almost 3,000 entries for Drake equation. What do you think? Do you think n is 0 or millions or somewhere in the middle? And if you're saying to yourself, well, Nora, if n is in the millions, why haven't we seen any aliens yet? Come back next time when we discuss the Fermi paradox.